to you, Max. If you would like to share your screen, I just have the title slide up on here.
All right, great. And we'll go ahead and get into it. So thanks so much for having me. I'm really excited to tell the group, the MxD membership, about all the great work we've been doing on the Integrated OPA Testbed. And before we get into it, I'll introduce myself. So my name is Max Toothman. I'm a principal engineer and principal investigator for this project, and I'm representing Applied Dynamics International, or ADI. And then we'll hear from Firas from Siemens a little bit later on in the presentation, but this project is also a collaboration between ADI, Siemens, of course, but then our colleagues at the University of Michigan, and then inspired by and advised by some colleagues at Dow. So very thankful for all the contributions there. We'll go ahead and jump in. So this is a good overview of most of the major topics we're going to hit on today, actually, but as a bit of a preview, I'll just mention we're going to be talking a lot about the business case for this project, the Integrated OPA Testbed, in particular about some exciting new technologies in distributed control, data analytics, and AI capabilities, but then also discuss some challenges that the legacy architectures of a lot of manufacturing systems present. And so there seems to be a little bit of a slower adoption of these advanced capabilities, and we think that's due to limitations around interoperability and data access that a lot of companies have. So in an effort to address those limitations, there is a new effort that's been underway for just a couple of years known as open process automation. And that spans a bunch of different technologies and approaches, but in general, it's a process control approach that prioritizes communication and interoperability between equipment from different vendors. So then this project is one of the first real practical implementations of a lot of OPA concepts, particularly across equipment from different vendors. So we're looking to showcase some of the principles of interoperability that OPA champions, show how that can be actually implemented in a real system, and then show all the different cool technologies and capabilities that OPA provides. So hopefully we get a chance to look at those in a lot of detail in this presentation. But I'll spend a little bit more time discussing the problem statement, kind of the motivations for this work. And we're really concentrated on some of the limitations that we've seen in traditional control and communication architectures. So what we've heard at ADI from some of our customers and from some of the different MxD members is that there are certain limitations, certain restrictions that traditional manufacturing systems just come with right out of the box. And that makes it difficult to both upgrade and iterate on existing systems, and then certainly to bring in new control, sensing, computing equipment to take advantage of all the advanced analysis, modeling, digital twin AI technology that has been rapidly advancing. And so because a lot of companies are in handcuffs with a lot of these technologies, a lot of the manufacturing data that they have been collecting is left unused, and then there are a variety of different avenues for further data collection that aren't even available. And so the net result is that a lot of companies aren't able to achieve the productivity, efficiency, and cost benefits that these new fancy technologies can promise to bring. And so the purpose for this project, our main goal, is to demonstrate how open process automation addresses many of those challenges and breaks down many of the barriers that limit adoption of new technology, and show how OPA concepts can promote interoperability, flexibility, and data access within a realistic manufacturing environment. And then in addition to that, demonstrate how OPA, an OPA-enabled system, can take advantage of these advanced process control, data analysis, and modeling capabilities. And I know we've got a diverse audience, definitely a diverse MxD membership that is interested in this type of work. So hopefully we can speak to the whole range of different professions and roles that we have in the audience and the membership here, from the more business-minded perspective or the more theoretical research-minded attendees. Hopefully we can speak to the benefits that open process automation can bring. So this would be advantages in productivity and cost, first and foremost. But then today we're also going to be talking a lot about how these technologies are actually implemented in a real system. So for the more operationally minded folks, we're going to be talking a lot about how data access can be free-flowing in these types of systems, and how a lot of the interoperability limitations that often plague manufacturing operations are broken down with an OPA system, and the advanced control and modeling strategies that that enables. Just a little bit of background for this work. So this Integrated OPA Testbed is the project I'll be talking on today, but that's actually an extension of two pre-existing testbeds that MxD owns and were completed a few years ago. So informally, we refer to these as the Part A and Part B testbeds. The Part A testbed on the left there is the digital twin testbed for process manufacturing, and that was a big project headed up by Siemens and Dow several years ago. And so that's been on the factory floor for a while now, and we're using a lot of the same hardware, as we'll see in a moment. But this is a realistic manufacturing system. It's closed loop, so it's not producing any product, but it has a 3-tank system that has oil and water in each of the tanks, and a central separation/mixing system. And even though it's not producing anything for public consumption, it has all the latest industrial equipment, valves, pumps, motors, things like that, and then a whole suite of Siemens' latest and greatest software that visitors to MxD can experience to see how those software platforms can be used for virtual commissioning, digital twin visualization capabilities like that. Now, the mirror image to that is the Part B project, and that was completed around the same time, and that was an effort headed up by ADI, so my company, and that was developed in partnership with the Part A project, but that is meant to be a fully virtual simulation-based representation of the physical system. And so it was housed within the ITE integrated testing environment cabinet that you see at the bottom there, and that has, like I mentioned, a virtual representation of the physical Part A system, and then a host of digital twin modeling analysis capabilities that are running on a Dell server inside that cabinet in the Adept platform that ADI develops. So this project, like I said, is an extension of those Part A and Part B project. And first and foremost, the goal is to bring those two systems together, which was always kind of the goal from the very beginning. So we wanted to augment the Part A process testbed with the computing and modeling capabilities that the Part B simulation system brings. And so we'll talk in a lot of detail about how we actually do that, but suffice to say, we establish an open communication network between the Part A testbed controller and the Part B Adept platform. We can see the PCS Neo and ADI's Adept platforms are the formal names for those. And then we use the open OPC UA messaging protocol to transmit information across those systems, so we can share process measurements collected on the testbed to the ADI system, and then send modeling results back over to the Siemens system. Now, in addition to bringing together those two pre-existing nodes or control and computing systems, what we also wanted to do with this project is show how an OPA-enabled system is fully compatible with cloud computing. So another big goal for this project was to integrate a cloud node into the communication architecture of the testbed and show how we can have cloud resources, in this case virtual machines, that are communicating in real time with our local systems. And so we do that by setting up a couple virtual machines in the Azure cloud computing platform. And then in a similar way to the local communication, we establish OPC UA communication just over the MxD firewall. And in this case, we're sending some local health metrics back up to the cloud. It has an IT monitoring framework model built into that computing platform, and then it sends the results back down to the local system. So you can see that on the screens that are at MxD. And so those are two major goals, or big lifts for the project, but they're mainly focused on communication. And what we definitely wanted to do with this project is not just show data going across, but show some of the capabilities and some of the advanced models that you can achieve and develop and deploy with that new free-flowing communication. So a last piece that we'll spend a good bit of time on in the demonstration section is a demonstration of advanced data analysis and modeling capabilities that, again, are only possible because we have an OPA-enabled system. So we can combine the best of Siemens process control capabilities with ADI's edge computing platform. So we'll touch later on an anomaly detection use case. There's several models, digital twins, that we developed for anomaly detection. In addition to that, we developed a fault injection capability that allows us to inject some drift into certain machine signals that we can monitor and then project forward to do some fault prediction. And those goals that I just mentioned are very much tied to our project success criteria and our KPIs. So open communication, obviously a huge focus for this project. We want to establish reliable communication between all of our nodes, local and cloud, in this project. And there we'll be monitoring things like the message throughput, message dropouts, and read-write times. We've got a panel in the top right that's a sneak peek of one of the visualization tools that we're using to show that open communication. Then from the data analysis and modeling side, a lot of work went into that. We are mainly focused there on things like model training and evaluation times, false positive and negative rates. Those are kind of industry standards for gauging the adequateness of a model, and it's definitely something we were paying a lot of attention to during model development. And then in addition to those two more technically minded goals, we also want to just spread the word, raise awareness about open process automation. And so that takes effect through events like this, all the documentation and education materials that we put together as part of this project. And we really have put a lot of work in to develop a unified storyline and a lot of display components, both virtually and on the factory floor for visitors, to demonstrate the value that OPA can bring to manufacturing systems. So now we'll get into some of the demonstrations, some of the product overview material, show what we've been working on for about a year now. And we'll be talking mainly about the integrated OPA testbed. And again, the key attributes here that we want to drive home are the interoperability, the flexibility, and the transparency of data that open process automation concepts can bring to a manufacturing system. And so what we're doing here in a nutshell is bringing together the previous Part A Siemens process skid with the ADI computing system, computing components that are housed in that ITE cabinet at the bottom there. And because we've been able to unite these systems, we're able to show real-time bidirectional OPC-UA-based communication between those systems, which again are running completely different software platforms developed by completely different companies. And then, like I mentioned at the top, we also have a cloud node that we're using to monitor the on-site equipment, and then a suite of digital twins that are responsible for use cases like anomaly detection, fault prediction. And these are just examples of the many different modeling and analysis use cases that are now possible if you have this wider choice of equipment that you can bring into your system. So this is another view of the testbed architecture and shows this in a little bit more details. And the key components to pay attention to are, first and foremost, the OPAS aligned connectivity framework. So this is our central communication bus that facilitates the flow of data between all the different computing nodes that we have here. And then down at the bottom are our main on-site nodes that we have touched on a bit already. At the very left, we've got the ADI local DCN, or DCN stands for distributed control node. And that computing system is responsible for a lot of our visualization, analysis, and modeling functions. So within that computing platform that's run on Adept, we have models dedicated to anomaly detection, fault prediction, as well as some local temperature power distribution sensing. And then, of course, that OPC-UA capability that allows us to communicate with the other systems that are part of this testbed. And then all the way at the right here is the very important Siemens DCN. And so this is somewhat of a new system, but the Siemens team did a lot of great work to open up their existing process skid that was originally operating in isolation, but did a lot of work to open that up to enable OPC-UA communication with the other systems that really highlight and make this testbed unique. And then up at the very top there is that cloud node that we've talked about. So that's responsible for doing some monitoring of our local assets. And again, that's running in the Azure cloud on a set of virtual machines, but it's able to maintain real-time bidirectional communication with our local assets. So we think that's a really good demonstration of the flexibility that this type of an architecture can provide. You can use cloud computing resources that are really easy to scale up and scale down as needed. And then, of course, at the very end here is the process skid. So that's the actual physical equipment that comes with the PCS Neo controller that Siemens provides. And then now to give a little bit more details on the Siemens specific accomplishments and developments for this project, I'll toss it over to Firas from Siemens.
Hello, everyone. And thanks for the opportunity here to present. And thank you, Max, for the great introduction and walking us through all of this so far. So yeah, from the Siemens side, when it comes to OPA, we demonstrated really how you can integrate a PCS Neo system or PCS Neo component together with OPA standards, with the OPA standards we have available, right? Which gives us, in general, also the opportunity to show really that we are driving innovation, that we are committed to openness and interoperability. We have been developing and supporting the OPA activities since the inception of the Open Process Automation Forum. From the technical perspective, looking at that, we did go ahead and developed an OPA-aligned DCN, distributed control node. That is one of the topics that Max already shared in the architecture drawing, where we're talking about the DCN. And of course, Max mentioned already the kind of interoperability between ADI and Siemens in this regard. So you have to imagine we're getting data out of a S7 system into an OPA-aligned communication with all the information models and sending this data over via OPA to the ADI colleagues. Which means that we integrated the existing hardware that was already on site into the whole OPA framework. Next slide. So how can you access all the software? And when it comes to PCS Neo, is it available? Yes, it's available. It's integrated. We are very proud of that, what we have done with PCS Neo. One of the major advantages you have that in addition to that, what's on the OPA side is that it's really a web-based control system, right? So it's accessible to all members. Put here a link how you can get into that in detail. If you have any questions, feel free to contact us. I save you all the time. Going through all the items, I think it's a very complex system. It's a complete control system with all the capabilities that supports interoperability and openness, especially with the topic of MTP, modular automation, which is also part of the Open Process Automation Forum, which is going to be or is part as a separate working group in OPA. Otherwise, again, feel free to contact us for any further details, how to access all of that. Again, we made it available with our original PCS Neo software and a special gateway, and also thanks to the colleagues from ADI, having really working together in the great collaboration. Otherwise, going back to you, Max, again.
Yeah, thanks a lot. And I'll just mention from the ADI side, all of our computing platform, a lot of the screenshots you'll see here today were built using the Adept computing platform. So that's ADI's edge computing platform, and that brings a lot of capabilities that enables projects like this. So the ability to bring in custom models from Simulink, Python, languages like that, and also plugins for a lot of the major aerospace and industrial manufacturing protocols. And if you'd like more information, feel free to reach out to me or anyone at ADI, and you can also contact that info at ADI for more specifics about Adept. And so, like we mentioned at the top here, so the project is closed out as of a couple weeks ago, and we buttoned up all the deliverables, finished our on-site testing and demonstration at an on-site visit a few weeks ago. So I'll just provide a quick glimpse into some of the project milestones. We conducted a set of reviews, requirements reviews, preliminary and critical design reviews throughout the course of the project, and those were usually held at one of our partner facilities, either Siemens or MxD. Development of the cloud node that was able to progress in parallel with a lot of the on-site efforts. So we were able to wrap that up relatively early on in the project and felt good about those capabilities as of about March. And then the on-site equipment installation testing is a little bit of a longer process, but wrapped up around April was when we felt really confident in that bidirectional communication between our systems. And then the remainder of that project time was buttoning up some final action items, but then a lot of model development. We worked with the University of Michigan group to train, deploy, and test anomaly detection models and fault prediction models that we'll get a chance to view in action in a couple slides. And we've got here a few more details into some of the major action items and progress items throughout the project. So at the top, preliminary design review, requirements review was very important for getting everyone on the same page. And then through a lot of the on-site network specification, installation, and modeling efforts that we've talked about up to this point. And then final demonstration, like I mentioned, happened on-site at MxD just a few weeks ago at the very end of July. All right, now we'll get into some material that we're really excited to show. So we've got a collection of screenshots and videos coming up that hopefully give you a really detailed view of what it's like to visit the MxD factory floor and see this new innovative testbed in action. And then at the beginning here, we've got a collection of photos. So this is showing the MxD factory floor and what the actual equipment that's on site on the floor looks like. And this has actually changed a bit from the original layout of the factory floor exhibit. So originally the MxD or the Siemens testbed was rotated 90 degrees, so it was facing that walkway. But in the April visit, we did a lot of planning beforehand, but rotated that system and then brought the ADI display forward a little bit. And that ended up in a footprint that we're pretty pleased with. We think it opens up a lot of the space and critically allows visitors to view both the Siemens display that borders the process skid on the left here, maintaining a sightline to that process skid while also showing the ADI ITE cabinet at the bottom here, and then our 3 monitors that we use to display the Adept application that show a lot of the modeling and data transfer technology built into the testbed. And then at the very top here, that's Nadia, who's an on-site employee of Siemens, but works at the MxD facility. And so she was a great sport about learning all the ins and outs of the testbed during our last visit, and then gave a really great final demonstration to the MxD team. So a big shout out to Nadia there. And then we've got a collection of screenshots, and these are actually videos that'll play in the background, but these are all interactive panels that if you go to the MxD factory floor, you can see these displayed on the 3 ADI monitors here. So we'll run through each of these and show all the real-time metrics that we're able to display here. So this really does a great job, this panel does, of highlighting the interoperability and the free flow of data that's core to the testbed. So what we have here is a real-time representation of the process skid. And this mirrors the Siemens HMI that the team built out for the previous project. So visitors to the factory floor can look at both HMIs and see in real time data, again, getting updated on one HMI and then almost instantly being reflected on the other HMI. So we're able to see how the same data is available to both the Siemens and the ADI systems. And then we've also got some animations built in here to show things like pumps starting to move, valves opening and closing. And then also worth pointing out on the very right here is the IT health monitoring metrics. And those are measurements that are computed by the cloud node. So we send measurements like the internal temperature of the system, some communication rate metrics back up to that cloud node, and then it does some processing, checks some limits, make sure nothing's amiss in the system, and then sends back metrics like the overall health state, the healthy or unhealthy state of all our different communication systems. So you can see those metrics there on the process panel as well. And then this is one of our subpanels that you can navigate to from the center monitor on the ADI display. But we really like this one because it drives home just the idea that there's always data flowing between our disparate nodes in this testbed. So we've got a diagram here that mirrors that architecture figure that I showed at the very beginning, but I'll just point out in this case, we've got real-time metrics, indicators of the messaging rates that are transferring between the systems. And so one in particular that's pretty interesting is this messaging rate from Siemens to ADI. And so that's variable because we're only sending new messages or updating the values on the ADI side when we sense changes in certain metrics. So this will tend to vary between 1, 10, 16 messages per second, just because every second, every cycle on the process skid, we're monitoring for updates in our measurements and then sending those updated values back over to the ADI side. And then we've got similar messaging rate indicators, metrics, for measurements that we're sending from ADI back to Siemens. Those would be modeling results and some control commands that we'll look at later on. And then similarly for the ADI cloud to the ADI local DCN. Those are exchanging messages at a rate of 5 Hertz. So hopefully that gives you an idea of the different communication capabilities that this new testbed brings to bear. And now I want to spend a little bit of time talking about the advanced modeling and analysis capabilities that this open communication unlocks for a manufacturing system like the one we have here. So we've got 2 use cases to look at. The first is anomaly detection that I'll talk about now, and then we'll get to fault prediction. But for the anomaly detection use case, what we wanted to provide here was a relatively simple application where we could collect data from the system, use that to train an anomaly detection system that essentially gives an up or down, good or bad indication of how the testbed is operating. So to do that, we isolated 3 controls that the operator has over the testbed. That would be the oil pressure set point, the oil flow rate set point, and the water flow rate set point within the system. And then somewhat arbitrarily, but we put bounds on what we consider to be normal operating behavior. And that was just based on how the operators from Siemens usually run the testbed when they don't want to show anything going wrong. So we established normal zones in the center of those allowable ranges and then designated the very ends to be anomalous regions. And then for the anomaly detection application, what we're able to do is run several tests at different combinations of those set points to get a good sized historical database for what normal behavior looks like, and then feed that into our data-driven model. In this case, that was a 1-class support vector machine. And what that's able to do with pretty limited human intervention or manual intervention necessary is draw a multi-dimensional boundary around those measurements. So then that gives you a representation of what normal behavior looks like. And then to get some actual use out of that, you can run that in real time with new measurements. And then the model will compare your new measurements that you're getting from the system with your historical base of measurements, and then give you, like I said, a thumbs up or a thumbs down indication of, is the system operating normally, like I've seen from the historical data, or is there some anomaly that's popped up? Is there some difference between this new data and the historical data that I've been trained on? So this is what we think is a really high value and relatively simple to set up modeling use case that a lot of manufacturing systems could benefit from. But like I mentioned, because that's it's a simple output, which is nice. It's a thumbs up or a thumbs down. But in the case where you get a thumbs down, that a problem does come about, most of the time, your next question is going to be, well, what is happening with the system? Is it going to be threatening? Do I need to intervene immediately? Or is this a benign problem that just wasn't included in my training data? And so to give some information, some diagnostic information on problems that do pop up, we developed a set of signal-specific diagnosis models. And so that's what this legend is showing the outputs of. So for each of our digital twin inputs, which are a collection of 6 signals we'll see on the next slide, we took just the measurements from that signal from our training data set and provided it to these random forest, isolation forest models. And then that's able to tell you on an individual signal by signal level, is a new measurement that we're getting from the system, is that similar or different from our historical database? So now you can laser in on certain problems that are popping up in a test bed, probably once you've been alerted by our more overreaching anomaly detection system that a problem is happening. So to give you a sense of how this works in a normal use case where we run through the different operating conditions that we've built the model to detect, we've got a quick video here that shows what the HMI for the adept application looks like on site. So I'll start that up, and then this will walk us through the major components of the testbed, or of this anomaly detection application. So on the very left here, we've got depictions of our digital twin outputs. So at the very top level, we've got one digital twin that has access to all the information, and that can give us either a normal or an anomalous output. And then in the case where we get anomalous measurements, we've got sub-digital twins that give you some more fine-grained information on what types of signals are showing anomalies. Then up at the top here, that is just a time series history of our top level anomaly detection digital twin. So that gives you a sense of how measurements are trending over time. And then at the bottom here are those signal diagnosis charts that I mentioned. So here we can see the whole set of all of our 6 anomaly detection inputs. And then the background in these blue violin plots, that's a depiction of what our historical data looks like. And then as we get new measurements, you will see in the video, the vertical lines will show real-time measurements that are coming from the Siemens testbed, and those will be green if we deem those to be normal with respect to that individual signal, but will show up as red, and the red border will pop up around the signal-specific plot when there are anomalies that pop up. And so in this initial state, we're operating the system completely normally, right in the bullseye of our normal operating zones, and we can see the high-level output is normal, and we're at 100% confidence. But then what we can do to show some interesting behavior here is raise that oil pressure set point, and we can see the results from our anomaly detection as we're settling into that new set point. So what we can see is that our high-level anomaly output is now anomalous, and we've seen a pretty steep drop-off in our historical anomaly detection history. And then to give even more context around what exactly is happening unusually in the system, we can look to our signal-specific plots, and that shows exactly what our set point change you would expect to see from that. We see higher oil level pressure measurements than we had previously seen before, and that also shows up in our oil pump speed readings and our oil valve position. So this is a good indication that something is going maybe not wrong, but something unusual is happening in the oil subsystem of the testbed. So that's an example of some of the anomaly detection outputs that you can expect to get from a system like this that's catered toward anomaly detection. And this is the type of application that, like we said, is relatively easy to set up and can provide some valuable diagnostics on what's going on in your manufacturing setups. But what we also wanted to demonstrate is because these data-driven models are inherently limited by the data that they have access to, a lot of times they require certain levels of upkeep or maintenance just to keep these up to date with the system, or maybe just to fill in gaps that are present in your normal or in your original historical data. So what we've built into this anomaly detection system is a fully automated model retraining setup. And so we can demonstrate this by considering if we wanted to add a new normal set point to our system. So in this case, just an example, we're going to expand what we consider to be normal oil pressure for the system. So we're going to essentially take that previous set point that was flagging all those anomalies and tell the model, you know, that actually, maybe that's relevant to a new recipe or a new process that we're adding to the test bed, or maybe we just forgot to put it in the original historical training data set, and we want to gather some data as it's coming in real time. We'll see how that works in a second, and then update the model with that new data so that it doesn't continue flagging that condition as anomalous and raising those false alarms. And so this is an overlay because this is happening on another panel off screen, but there's some HMI elements that allow operators to gather data that's coming in real time. So they can do that with one click by starting preparing of your retraining data. And then we cut forward a little bit here until we have enough retraining data for this application. But then we can cut off data preparation and then just one click retrain our anomaly models. And what that does in the background is retrains the models to generate new versions of the models with that new expanded training data set. And then once we do that, once we deploy that, which all happens in real time without having to bring any of our models or any of our operations down, let me rewind there, we can see is that now we're getting pretty high confidence in our normal output for the system. And we can actually look at, I think it's pretty interesting if we pay attention to the signal plots down at the bottom here. So like we would expect, we're seeing anomalous outputs for our oil pressure and our oil speed measurements. And then as soon as that model retraining takes effect, we can see now there's a whole big hill of measurements, grouping of measurements around that new set point. And then now we're no longer getting anomalous outputs for those application signals because we've added that new data into our anomaly detection system. So it knows that that's a set point that it doesn't need to be worried about or raise alarms in response to. So now we'll transition to the second of our modeling use cases. And we've also got a video showing the adept application in the next slide here. But just to set this up, this is a little bit more complex than our anomaly detection case. But what we wanted to show here was an example of how you can use data-driven models to detect the early stages of a problem within your system. So while the anomaly detection was telling you is something good happening in the system or is something bad happening in the system, with a fault prediction or a degradation detection system, that provides you with early indications that something might be trending in the wrong direction. So that's what this application is focused on. Now to do that, because we don't want to actually break anything or cause real degradation in the system, we developed a set of fault injection capabilities that allows the ADI local DCN to take control of one of our valves in the system. And when we've requested that access to the valve and Siemens grants access to the valve, what we can do is we can choose to slowly open or slowly close that valve, which has ripple effects on the flow rate that we see that valve is controlling. And now critically, the rest of the testbed doesn't know that we've taken control of that particular component. So the set point stays the same. And then what we see and the metric that we're going to be tracking is what we call the flow error, which is the set point minus the measured. So as we change manually that oil valve position, we're going to start to see non-zero values pop up in our flow error. And that's the trend, that's the signal drift that our fault prediction model is looking for. In this case, we can diagnose either error increasing or error decreasing behavior. And then the fault prediction model behind the scenes is estimating what that degradation trajectory is. You can see an example of that with this orange line. And then it's extrapolating that into the future through some probability calculations. And we're getting a probabilistic box and whisker plot that's projecting when we're going to hit our upper fault threshold. So that's our definition of a fault in this case, is a oil flow error that exceeds some absolute value. That's the condition that we're projecting out towards. So we can take a look at what this looks like. Again, from the adept application that's on the factory floor, this is on the same screen that shows anomaly detection, just in a different subtab. But at the beginning here, we're showing the process of going through and requesting access to that oil valve that stirs the drink of our fault injection. So here what we're doing is we're requesting access to the valve, and then we're telling it to increase slowly the valve position, in this case, 0.3 percentages per second. And then we can enable fault prediction to tell the system to begin monitoring our flow error metrics and looking out for degradation. So then what we see at the right here, mirroring the legend that we saw in the last slide, we've got real-time data on the deviation from our set point. That's the flow error here. And then at the bottom, similar to the anomaly detection case, that's a historical chart of what we think our most likely stage probability is. So as we get deeper into this, we'll see degradation pop up, and we'll see that orange line go right up to 100% confidence. That's what we see here. As we are slowly opening that valve, we're beginning to see deviation from a flow error of 0. And then it takes a little while, so we speed this up just for the sake of the presentation here. But pretty soon we've encountered a step change, and now we're going to start to see some dynamic behavior in our oil flow measurement. And at that point, the fault prediction model starts to estimate the rate that we're degrading, the rate that this flow error signal is decreasing. And that's the orange line is our estimated degradation trend. And then at the top here, that's the results of the fault prediction. So what we're doing is we're extending that estimated degradation trend forward in time and providing a probabilistic description of when we expect to hit that critical fault threshold, either upper or lower. And what we're seeing at the top here is a box and whisker plot, and the edges there are showing the different percentile predictions of our fault prediction. So we can let this play out, and then we can see how our prediction changes, again, in real time in response to new measurements that we're getting from the system. And we're going to start to approach the fault prediction threshold pretty soon here, and that's going to cause our estimated fault time to get pretty close to our current time. Until we see at the very beginning here, that's when we hit our fault threshold, and then our oil flow digital twin output is faulted because we've already passed that critical threshold. So hopefully that gives you a chance to see and experience in real time a lot of the advanced modeling and analysis capabilities that, again, are only possible because we're able to combine the strengths of the Siemens process control system with ADI's edge computing capabilities. And so transitioning into the last few slides here, a lot of work has been done lately on project transition. And I'll point out just a couple education deliverables. Naturally, the physical testbed is equipped with all sorts of signage. We put a lot of work into the HMI to try and provide context into the different computations that are happening. And then as part of the deliverables for this project, did a lot of networking, software development, documentation, explaining to MxD members and the MxD engineers how things work, and so on and so forth. And then, like we mentioned at the top, one of the big purposes or goals for this project is testbed documentation and some publication of OPA. And as part of that, we have an open process automation report that sums up a lot of the lessons learned and the recommendations, suggestions, guidelines from this effort. And then, of course, the main technology deliverable is the OPA testbed that's physically on site at MxD, and all the Siemens and ADI applications that make everything run. Brings about the HMIs and the visual displays that we just saw. So there is, like I mentioned, a lot of documentation, some education material that we're really excited to share with the community and with our partners as part of this project. And I'll give a couple highlights as far as technical lessons learned here. Because this is an interoperability focused project, there are a lot of teams that were brought together from MxD, Siemens, University of Michigan, ADI. And so one of the really valuable steps that we took early on was a lot of meetings, a lot of discussions and site visits that were aimed at standardizing and defining the information models based on the data that we were passing back and forth. And that, along with some detailed definitions of the networking plan, really made our lives a lot easier as we got on site and started installing all the components and testing communication. It was really important that we were handling data in the same way, doing things like expecting the same data types and the same sampling rates. That really makes your life easier when you're actually on site implementing and testing everything. But I think this project also shows a couple challenges that are just going to be unavoidable in industry as open process automation starts to take hold and get wider distribution. A big problem that we actually were faced with in this project was interfacing with traditional control and computing equipment. And like I mentioned, the Siemens system, the process skid, was pre-existing, so that was already on site, having been built a couple years ago. But what is a good strategy that doesn't require you to completely scrap your existing operations is implementing gateway systems or developing gateway systems. And that's actually what we're using here, is a Siemens developed gateway that gathers data from the legacy control and computing equipment that is in charge of operating the skid, and then translating that into OPC UA information models that then other nodes from different vendors can access. So I think that's a really powerful solution that, again, doesn't require operations to completely scrap existing systems, because that's just not practical in almost any situation. And then another challenge that we saw, and I'm sure is going to be widespread in the industry, is different implementations of communications software. So there's a variety of different standards and best practices that are popping up to facilitate this sort of OPA-enabled communication, but there's always going to be some differences in how companies implement certain high-level concepts. So frequent interoperability testing that we did at MxD sites and even at the Siemens sites, that was really valuable to make sure that when we were on site that all of our equipment was speaking the same language and considering or expecting the same information to be passed between the different computing nodes. And I'll wrap up here by giving some involvement, some extension information. So like I mentioned, we're really excited to share the results of this work and to give more details to the MxD membership. We think that's a really powerful network to try and get some information and drum up some enthusiasm for this effort. And we're very interested in any feedback that the audience for this call has on the project or even just the higher level problems, motivations that we talked about at the very beginning. So if you have any information, thoughts, feedback, further questions, we're happy to accommodate that to get whatever information you need. There's some more information at the QR code and at the website listed down here. And then we are really excited to leverage the MxD network to generate some ideas for project extensions. So that can include existing or new capabilities that we implement on the MxD system, but ideally would be some further applications at partner sites. So because this has some limitations being a demonstrator system, it would be really great to try and extend the same type of technology that we demonstrate here to actual production systems, get a chance to see what the differences in those applications are, and then continue to improve the product, but then also to get some more specific use case, specific information on how this can generate value and improve operations for different customers. So if you have any information, would like to reach out about any of that, or like I said, have any questions about the material we discussed here, you're more than welcome to reach out to myself. Joe Manley is my colleague at ADI, who would be a great point of contact. And then Firas from Siemens that we heard from earlier, as well as Harris, who was really instrumental in this project from Siemens. And with that, I'll close out the presentation and be happy to answer any questions or give any more information that folks are curious about.
Max, if before you start Q&A, I'd like to do a couple shout outs.
Yeah.
I'll introduce myself. I'm Scott James. I'm ADI's president and CEO. I see that Joey Hess and Brian Clemens and Caitlin Dubois, all from Dow, are on the call. Those three were instrumental in many phases of the Part A, Part B, Part C project here, but also contributed in a big way to the testbed requirements that we developed over a summer in the middle of COVID. So great to see everybody.
Hey, Scott, it's great to see you too, and happy to see these two systems combined. We did so much early on with these two projects running in parallel, and we were always chomping at the bit to see what they could do together. So very nice presentation.
Same here.
Yes,
Glad to
great
see
work.
everything finally came together at the end.
Yeah, it's incredible to see, to know where we came from and what we have now. Just wonderful work.
Yeah, and big thanks, Max. Incredible work as principal investigator on this. So with that, I'll pass it back to you for Q&A.
Thanks everybody for obviously the presentation and all the work you did on this project. I'm just going to kind of MC the Q&A here as Nitin in the chat asked a handful of questions. So kind of off the bat, a question on latency and lag with the cloud when you're doing real-time interactions. And I'm not sure, Max, if you have access to the chat, but Nitin asked a few extra questions on the option for not using the cloud, interfacing to simulate possibilities, and how you can interact with the real-time physical system through your interface. So a few things on kind of how real-time the latency is, and then different capabilities to interact with the real physical system.
That's a very good question. Let me scroll back to the communication platform, just talking some specifics about the communication rates we're dealing with here. But that's definitely a very good point about the lag that comes with cloud communication. So we actually ran into that because our logical devices, which is how we enable OPC-UA communication, we can set those up on a local system, 2 servers right next to each other to talk at really high speeds, 100 hertz, probably even faster. And so we expected to bring over some of those logical devices and get that really quick communication with the cloud node. And we saw pretty soon that we were getting overruns, computations were taking longer than we expected, which makes sense because we're going over the internet to a remote cloud platform. So the messaging rate that we felt confident on, and this is probably a little conservative, we could push this up a little bit if we really wanted to push things, but we're still able to get 5 messages a second back and forth between the local DCN and the cloud DCN, which we think is pretty good for a lot of applications. Maybe not if you need really high dynamic, really low latency, and you want to have that in the cloud for some reason. But in that sort of a situation, it's probably best to have a local asset doing those really critical calculations. And then for air gap facilities, yeah, go ahead, Scott.
I was going to say, just for some context, I don't think I heard that the ADI local DCN here it's a Dell powered server, right? It's running real-time Linux, and then it's running the Adept edge computing services, which are very tightly tuned, but highly optimized. So they're about as low as you can achieve. So it's a good test. And then of course, the system. Do you know what specific Azure server profile you were using? Because that can have a big impact.
It's a couple Linux virtual machines.
Okay, yeah.
But yeah, the real bottleneck is just communication over the internet through the MxD firewall. If you have local systems, you can get really high frequency communications. And then to the other question for air gap facilities, a no cloud option. Certainly the cloud node we just implemented for the system to show that this was possible. If you have high security applications you don't want to bring into a cloud node, there's certainly no reason that you would have to. So you can do all the computations, all the modeling that we're doing here with on-site assets if you don't want to deal with the cost or the hassle of setting up a cloud node.
Yeah, and I think that with most of the projects we've been involved in, on-premise is the preferred way. Cloud is still not quite there, but the potential it offers if you need that kind of computing scalability is big. But cybersecurity is overruling, I think, the day.
Yep. And then I think another question from the same person, another good question that I'll speak to. The interface, can it be used to interact in real time with the physical system? Definitely yes. And so the fault injection is a good example of how we're doing that real time interaction with the on-site assets. So what we're seeing at the very beginning here, the first step that we do for fault injection is request control of that valve that is operated by Siemens. And so that's sending in real time a request to the Siemens system to take over control. And then once Siemens does their due diligence and accepts that request, then what we're able to do is send control commands to that oil valve and control it directly from the ADI system. So it's not only that we have visibility into what the Siemens system is doing, the measurements that it is recording, but we can also take control action, which again would only be necessary in applications where that makes sense. You certainly don't have to open up all the controls to us, and we don't have that in place here, but where it does make sense and where it would bring benefit to the application, we can certainly make that possible like we've done here.
Awesome. Appreciate you getting to those questions and some good responses on those. Nitin, feel free to follow up offline as well if you have some more detailed questions. And then I saw the question in chat from Derek Heiser referencing similar work that SESME is doing. Curious if you have any notes on how the two things overlap or can complement each other. Otherwise, this might be a good opportunity to take something offline, not to cut off conversation here, but knowing that we're getting close to the end of the hour. Any quick thoughts on that note from Derek in the chat?
Yeah, so I'm looking at the UA cloud libraries. So any resources or a template for what these profiles look like. So specifically for our OPC UA communication, we do use some open source libraries, and some of my colleagues at ADI would be more qualified to speak about the details there. So feel free to reach out if you want any computing or coding resources for how we implement things. But Siemens is also extremely well versed in the OPC UA communications that we're using here, and they have some really well developed resources and can probably share more specifics as well.
Yeah, yes, for us. So maybe one thing to mention here. So SESMI and OPA, they are working kind of together, but on various streams, where SESMI is focused more on the OPC cloud library, and where we have on the OPA part or on Open Process Automation Forum, focus really on the information models that are specifically being transferred and given to the OPC Foundation. Let's put it this way to answer that question. They know about each other. I think there was some discussion about even doing a liaison agreement between those two, but at the moment they are somewhat independent. Of course, the underlying OPC Foundation is the foundation that where everything comes together. But at the moment, the work that's being done in SESMI related to the cloud and the cloud library is not incorporated in OPA or part of the OPA forum. I hope that answers the question.
Yeah, and then on the other half of that question, on the OEM communication, I think it's probably going to be a mixture of both, and that speaks to who is on the hook for promoting or implementing these technologies. I think it probably depends on how much expertise or how big of a team a manufacturer has. Maybe they have the resources and the weight to develop some of this in-house. But certainly, I think in a lot of cases, especially for existing systems, it's going to be efforts by the OEMs, by equipment providers, or by companies like ADI that bring in some expertise on how to implement these interoperable systems and can bring a lot of good benefits for existing systems.
Yeah, and one thing to the SESMI topic, there is an event coming up where SESMI is probably even in MxD, where ADI and I, Joe Manley from ADI and me will be there as well. So yeah, just FYI, so we are aware about what SESMI is doing and what we will be doing in collaboration with all of this. So if you have any questions, please feel free to reach out.
Okay, great. Thanks again to ADI, Siemens, the entire project team, all the collaborators. I know you mentioned University of Michigan and Dow providing some of the work, especially early on in the earlier phases of this. Great to see, kind of what the collaboration at MxD can produce. So we will be following up with meeting slides and recording. I believe either via email or it'll be made available through the MxD member portal. So look out for that. And we'll look forward to seeing you all in future presentations as MxD continues to do more work in this space and generally in digital manufacturing. So thanks everybody, and have a good rest of your day.